Hello, everyone. Welcome to the webinar on air scrubbers. My name is Justin Stewart. I'm an applications engineer with Evoqua Water Technologies Municipal Services, and I'll be your presenter today. This is part 4 of our 5-part webinar series on odor control solutions for safety and stewardship. Today we'll be reviewing the different types of air scrubber systems and how they can be used for vapor phase odor control. And the next webinar will be covering oxidizers and iron salt solutions for reducing hydrogen sulfide to safe levels and to prevent corrosion. So today, as part of our discussion on air scrubbers, or what sometimes we refer to as vapor phase odor control, we will be covering the following key topics, mainly what do we mean when we say vapor phase odor control, and the 3 main types of air scrubbers, which are chemical scrubbers, carbon adsorbers, and biofiltration. And for each technology, we'll provide some background information, a description of how the technology works, and the application guideline for that technology. So what exactly do we mean when we say vapor phase odor control? So for those of you who have been to our previous webinars, you should be familiar with using chemical products such as bioxide or alcogen for eliminating odors in the wastewater. But instead, when we talk about vapor phase odor control, the whole idea here is not really to do anything about the odors in the wastewater, but instead to contain and capture the odors that have escaped into spaces such as wet wells or manholes. First, what we do is we ventilate those spaces with a blower so we can create negative pressure or a vacuum inside those head spaces, and then pull the foul air through an air scrubbing system so that way it can be treated and then released to the environment as clean, odor-free air. There are a couple different ventilation rates that we use here. The first is 6 air exchanges per hour for standard odor control applications. And if the space we are ventilating happens to be a continuously occupied structure, such as maybe a dumpster room or a biosolids handling area at a plant, we could instead ventilate, or we will instead ventilate those at 12 air exchanges per hour to make sure that that area is safe to work in. So in today's webinar, what we want to do is focus on this black box area that we're calling the air scrubber and the different technologies that we can put into use here. And when it comes to air scrubbers, there's mainly 3 types of technologies out there to discuss: chemical scrubbing, carbon adsorption, and biofiltration. The first technology we will be talking about are chemical scrubbers. Chemical scrubbers are a type of air scrubber that use a combination of sodium hydroxide or caustic solution and sodium hypochlorite or bleach to first dissolve odors and then oxidize those odors so that the air vented from the system would be free of nuisance smells. One of the key benefits of this technology is that it can actually handle very large airflows and high odor loadings. Essentially, as long as the system is sized correctly for airflow and enough chemicals are being fed to meet the odor load demand, these units can perform exceptionally well. And in addition to hydrogen sulfide, these systems are also able to remove a variety of compounds, including volatile organic odors. So if you have odors beyond just the hydrogen sulfide odors, these systems work very well. However, one of the big drawbacks of these systems is that they do have a lot of working components. So we have recirculation pumps, blowers, chemical pumps, pH probes, ORP probes, and controllers. And because of this, these systems usually do require a higher level of technical expertise to operate and keep maintained. Here we can see an example of the process flow diagram for a typical chemical scrubber. And what we see here is that foul air is being brought in from a headspace through an air exhaust fan, and then it passes through a number of different stages. The first stage in a chemical scrubber is what we commonly call the pre-treatment stage. And then after this, we can have anywhere from 1 to 2 or possibly even 3 additional stages for odor removal. And that really depends on what level of efficiency we need. And as I mentioned on the previous slide, there are a lot of additional control components here. So each stage has a recirculation pump to recycle processed chemicals. And we also have pH probes and ORP probes to tell the caustic and bleach pumps when they need to turn on or turn off. So now let's take a closer look at exactly what's happening in these different stages of the chemical scrubbing system. So the first stage of a chemical scrubber, like I said, is what we commonly call the pre-treatment stage. So during pre-treatment, you have that foul air that's being brought into the system that contains hydrogen sulfide or other odors, and it comes into contact with caustic solution. And if you happen to be watching last week's presentation on pH shift technologies or alcogen solution, this concept is very similar here. So the graphic might seem familiar. But basically what we're doing here is we're actually elevating the pH with caustic so that hydrogen sulfide gas will shift into a dissolvable form, such as bisulfide or sulfide. And then once it's been dissolved, it can then easily interact with bleach in the stages after pretreatment for odor control. And typically for scrubbers, we aim for a pH over 9 to try to convert all of the hydrogen sulfide gas into these dissolved forms for a more efficient odor removal process. So then once that pre-treatment has occurred, these dissolved sulfide species are then allowed to mix with bleach solution in the odor removal stages. And then that bleach solution will then oxidize the sulfides based on the following reactions. So if the pH is between 7 and 9.5, those sulfides are oxidized into elemental sulfur. And then if the pH is higher than 9.5, the sulfides will instead be oxidized to sulfate. And over time, though, the elemental sulfur that is generated in this reaction can start to build up on the packing media inside the system. And so because of this, we will need to routinely acid wash the equipment to remove any kind of built up solids that might eventually reduce overall efficiency. And as a guideline, chemical scrubbers are best used where we're observing those high hydrogen sulfide loadings and where organic odors might be present in addition to your typical hydrogen sulfide odors, and where a high level of odor removal is required. Also, if we have odor loadings that are intermittent or variable, these systems will work well since they can essentially be turned on when the odors are present and then turned off during downtime. This is something you might see in a biosolids handling process that will only operate on specific days of the week, for example. And some of the things we do need to remember and evaluate before we implement a chemical scrubber is that there is a higher capital cost related to all of the working components in the system. And we also have to have a high level of technical expertise to operate and keep these systems maintained. And again, there's also that periodic acid washing that might need to be done to remove any built up solids, and also have that understanding that caustic and bleach solution are considered hazardous chemicals to have on site and to have to work around. So moving away from chemical scrubbing, the next technology we're going to cover are the carbon adsorption systems. So comparing this to the chemical scrubbers, the carbon adsorption systems are actually much more simple in design and principle. And essentially what's happening here is foul air that contains hydrogen sulfide or other organic odors is passed through one or more beds of carbon. And if we take a closer look at the carbon in these beds, we can see that the carbon is actually extremely porous on a microscopic level. And these pores create a lot of surface area, and odors will actually tend to stick to or adsorb to the carbon and remain trapped inside these pores. This actually will then allow clean air to pass through the system and then be vented out of the air scrubber. These systems, the carbon systems, they're relatively simple to operate and they only require regular service to make sure that blowers are working correctly. And also we need to have a sampling to make sure that the carbon beds are not spent. And once those beds are spent though, we do need to have a routine media replacement to swap out the old carbon with fresh carbon. And because the hydrogen sulfide concentration will impact how quickly that carbon gets spent and how quickly it needs to be replaced, we typically recommend to use carbon systems for sulfide levels that average less than 10 ppm or so. Otherwise, the carbon just gets burnt through too quickly and you have to change the carbon out a lot quicker. So here's an example of a process diagram for a single bed carbon adsorber. So just like with the chemical scrubber, we have that foul air being brought in from a headspace through a blower. But then from here, the foul air is blown through activated carbon, and that's where the odors become trapped. Along the media bed, we also include sample ports so that way we can test the sulfide saturation at the inlet, middle, and outlet of the bed. And this gives us an idea of how much longer the carbon will last before it needs to be replaced. So for a single bed adsorber like the one we see here, we can treat lower to moderate airflows up to 6,800 CFM standard. But if we need to treat a higher airflow, we can use what we call a dual bed adsorber. And essentially a dual bed adsorber is just adding in a second carbon bed to the design, which allows for more carbon and more airflow in a smaller footprint. Although these systems, though, they are somewhat taller since they do now have two beds. The dual bed adsorbers are available as large as 20,000 CFM as far as standard units are available. And when it comes to the media options that we have, there are a variety of activated carbons out there. So in Evoqua Municipal Services, we offer the following standard medias for odor control applications. The first media, which is known as Midas OCM, is a pelletized carbon that's derived from bituminous coal. And this carbon is our high hydrogen sulfide capacity media, and it's able to carry about 67% of its own weight in hydrogen sulfide. However, Midas OCM does not really handle organic odors that well, and it is mainly specialized for the control of hydrogen sulfide odors. On the other hand, Vocarb P60, which is another pelletized carbon that we derive from anthracite coal, it handles organic odors moderately well, but it has a much lower capacity for hydrogen sulfide. So comparing that to the Midas, it's only about 6% by weight capturing capacity for hydrogen sulfide. But Vocarb P60 does have the benefit of being a lower pressure carbon, so that might be helpful for an existing system that is experiencing issues with air handling or with the current blowers, pressure losses with the current system. And then lastly, we have Vocarb 36C, which is a granular carbon that we derive from coconut shells. And these coconut shell carbons actually have a high capacity for organic odors, as well as a moderately high capacity for hydrogen sulfide at nearly 19% by weight. And as a guideline, carbon systems or carbon adsorption systems, they're best used for average sulfide loadings less than 10 ppm and where organic odors might also be present. And just like the chemical scrubbers, these systems can also be used in applications that have variable or intermittent odors and where less labor intensive equipment might be preferred. However, we do need to keep in mind that some labor is required for regular media replacement every 1 to 2 years or so. And during this process, the carbon will need to be tested for safety and disposal considerations. We also need to make sure that we're using an appropriate choice of carbon media based on the level of odors that need to be treated. And then lastly, with some types of carbon, mainly Midas OCM, the humidity of foul air can become an issue. So we do need to include a mist eliminator before the carbon vessel to keep moisture from entering the system. And then last but not least, the final air scrubbing technology that we'll be covering today is biofiltration. So biofilters and biotrickling filters, or what we call BTFs for short, they encourage the growth of specialized bacteria under controlled conditions on packed media inside of a vessel. And then foul air will be passed through these systems where it can come into contact with the bacteria. And then these bacteria will then biochemically oxidize the sulfide and remove it from the air. And then when you compare these to the other technologies, biofiltration is considered a relatively green or an environmentally friendly process because it does not require the use of hazardous chemicals or require the disposal of media. So now let's take a little bit of a closer look at the bacteria that's actually, doing the work cleaning the air in these systems. The full name of the bacteria is Acidothiobacillus thiooxidans, and it's known as what is known as an extremophile, or it's a naturally occurring bacteria that's able to thrive in severe and harsh conditions. And specifically for this condition, it's able to survive and thrive in high hydrogen sulfide concentrations. So for most species of bacteria, hydrogen sulfide is actually considered toxic, but for Thiobacillus, it actually needs hydrogen sulfide to survive. And as part of its metabolic process, it will actually consume that hydrogen sulfide in the presence of oxygen, and it produces sulfuric acid as a byproduct. So when you're talking about these biofilters, though, it's important to realize that these systems do contain living organisms, and they will require appropriate care to keep those bacteria alive. And so these main things that we need to look at are that the water is clean and free of disinfectants, that spray patterns are adequate to water and cover the entire bacterial bed, that the blower is maintained so that way we can provide a continuous supply of hydrogen sulfide to the bacteria, because essentially if you cut off the supply of hydrogen sulfide to the bacteria, the bacteria will start to die off because they're starving that hydrogen sulfide that they need. The bacteria also need nutrients as a food source, and for more northern climates that have colder winters, sometimes we do have to have a special consideration to keep those temperatures maintained and prevent the bacteria from freezing during winter months. And then lastly, since the bacteria is producing a sulfuric acid solution, the system does have a tendency to become too acidic if it's not watered correctly or if it's just allowed to um, run without any kind of monitoring. So for that reason, we do need to keep the pH optimized to a level of 1.8 to 2.2 by adjusting and monitoring our watering rates inside these biofilters. So one of the great features of the modern biofilter design is that they are modular. And by that, I mean that they're actually factory assembled and mounted on skids that makes them pretty easy for installation. So for example, if a municipality is interested in using a biofilter for controlling odors at a lift station, as long as a level foundation is provided with the correct dimensions, the skid mounted system can actually be shipped to the job site and then easily just set into place. And then all that would be left afterwards is to connect to a water supply, connect to power stub ups, and then run ducting between the draw point and the blower. And then once the system is started up and within 2 to 3 weeks or so of startup and carefully optimizing those water and nutrient rates, you could have a fully acclimated biofilter. Also, these systems are multi-stage in design, where the first stage is always an inorganic media that acts as that substrate for the biology to grow. And then the second stage can either be more biological media, or it can be a carbon polishing stage that can scrub any residual odors that might get through the first stage. And typically we see about 99% removal of hydrogen sulfide through the biological stages. And these systems are usually designed for 100 ppm average loading with a peaking factor of 4x or 4 times that average. Now, you might have noticed that I keep referring to two types of systems. So there's the biofilter and the biotrickling filter, or BTF for short. And hopefully not to complicate things, but the topic of biofiltration actually does cover two types of system designs. But it's important to know that while they might have their differences, they both actually operate on the same fundamental principle, which is encouraging the growth of that thiobacillus bacteria inside the vessel to grow and consume hydrogen sulfide. However, the main difference between the biofilters is that and the biotrickling filters is that biofilters have 1 to 2 stages of biological odor control, while BTFs can have 2 to 4 stages. And for the BTFs, having more stages, this actually helps promote the growth of a wider range of bacterial species in the BTF for targeting a variety of odorous compounds. And then also in biofilters, we can have an optional carbon polishing stage, while BTFs usually only have biological removal stages. Also in biofilters, the water and nutrients will pass through the biological stages a single time and then be drained from the system. But for the BTFs, we have a recirculation pump that recycles a fraction of that water and nutrients to make water and nutrient usage much more efficient. And then lastly, for biofilters, biofilters are normally sized for lower to medium airflow capacities, and the largest standard unit available for a biofilter is 5,000 CFM. And then for biotrickling filters, these are sized for medium to high airflow capacities, with the largest standard unit being 18,000 CFM. So here we have an example of the process flow diagram for a typical biofilter. So foul air is brought into the system through the blower, where it can then pass through the biological stage. And then as the foul air passes through that biological stage, pumped in water and nutrients will flow down through the bacteria, eventually reaching the sump and then be drained off. After that first stage, we can either have a second biological stage, or we could have a carbon polishing stage like we have shown in the drawing. And then once the air has passed through the system, the odors will effectively be removed, and then the air can be exhausted to the atmosphere. On this drawing, we also show an optional prehumidification step, which is useful in more colder climates for prehumidifying and warming the air before it reaches the biology. And then now for comparison to the previous slide, here we actually have the process flow diagram for a biotrickling filter, or a BTF. And as you can see from the photo in the right, these systems are generally larger than the standard biofilter design and are usually installed at wastewater treatment plants or master pump stations where airflows or loadings might potentially be very high. But in this diagram, the main difference from the previous slide is now we actually have multiple stage of biological removal shown, as well as the addition of a recirculation pump for recycling the water and nutrients through the system. And we do need to monitor the pH of the sump to make sure that's not too acidic. And then to prevent the buildup of sulfuric acid, some of that processed water that's being recycled does need to get drained out. But for every gallon of water that we drain from the system, we do have to make it up with a fresh makeup water supply. So in summary, for biofiltration, both biofilters and BTFs are best used where we have a steady and reliable supply of hydrogen sulfide. And then because we need to keep in mind that these bacteria do need the sulfide to survive. And then also where 99% removal of hydrogen sulfide would be considered acceptable. And these next items are actually becoming big factors for a lot of municipalities, but where safety is a concern because these processes don't use hazardous chemicals, and they're also considered green or environmentally friendly technologies, so wherever those might be preferred as well. However, we do need to remember that the typical design is based on an average of 100 ppm H2S. So if loadings are greater, we tend to have to derate the airflow from a larger system so that way we can handle the increased sulfide concentration. And then also the hydrogen sulfide concentration should not peak to 4 times greater than the average concentration in order to prevent any kind of odor breakthrough. And then lastly, these systems will require routine surveying and of conditions such as airflow, sulfide loadings, pH, nutrient rates, and watering rates to make sure that those bacteria are living in an optimal environment. So now I know that's a lot of information to cover in such a short period of time, but now to wrap everything up that we learned today. So the key takeaway is that vapor phase odor control applications, our main objective is to capture and contain foul air so it can pass through an air scrubber system and remove those odors. And then of the air scrubber systems, we have those 3 main categories of technologies: the chemical scrubbers, which use the combination of caustic and bleach solution for dissolving and then oxidizing odors from the foul air; the carbon adsorbers, which use the porous activated carbon to absorb and trap odors within the media; and then lastly, biofiltration, which encourages the growth of bacteria inside a vessel that will biochemically oxidize odors. Our next and final webinar will be on oxidizers and iron salt solutions, and will be presented by Nick Swanson on August 5th at 12 p.m. Eastern Standard Time. And we hope that everyone here today can tune into that presentation where Nick will be teaching about these 2 liquid phase odor control technologies. Again, my name is Justin Stewart, and you can reach me at the email address shown above, or you could contact our product manager, Calvin Horst, if you have any questions about today's presentation or any future presentation.
Thank you, Justin. We have a few questions that have come in so far. First question, there was a reference to a 4-stage chemical scrubber. When would multiple stages be required for chemical scrubbing?
So that's an excellent question. So typically with a chemical scrubber, so if you have a single stage system, the typical removal for a single stage scrubber is about 90% removal. Adding in a second stage, the removal efficiency goes up to about 99%. Adding a third stage, you can effectively get 99.9%. So essentially, if you have a very sensitive location where you need to achieve, essentially 100% control of odors, that's usually where you would get to the point that you need to have a possible 4-stage. But it's usually not that common to see because generally a 3-stage scrubber with 99.9% removal is considered effective.
Yeah, and to add on to that, complex odor profiles, may require the need for additional scrubbing stages. For example, if you need to remove ammonia and hydrogen sulfide, you need to establish different sets of conditions.
Yeah, that's a good point.
Next question, the biofiltration illustration is a rectangular tank, and I think we're talking about the Zavox there. Has Evoqua moved away from the vertical cylindrical towers? So we have a number of different air scrubbing capital solutions. So the taller cylindrical units. Justin identified those as the BTFs, and the rectangular one is the ZBox odor control system, and then the other smaller cylindrical unit is the Whisper odor control system. So the need for different, I guess, shaped biofilters is driven largely by footprint requirements and loading requirements. So there may be an opportunity to consolidate solutions at some point in the future. But really the aim here was to balance footprint with serviceability with cost, and that's why there are a number of different solutions there. The next question, Justin, is it possible to use carbon adsorption for H2S levels above 500 parts per million? Can you just add more filters to account for higher levels, and how often do filters need to be changed?
So yeah, that's a good question. So it's similar with the biofilters. How I mentioned, if you have for a biofilter, the design average is 100 parts per million. For carbon systems, the design average is 10 parts per million. If we have very high loadings, we would essentially have to, instead of using a system that, so like let's say you need 200 CFM of airflow, but you have 500 parts per million of hydrogen sulfide. You could not use a 200 CFM unit there. You would have to look at the ratios from the design average to what the actual average concentration is, and then upsize the airflow. So essentially use a larger unit, so that way you can capture the total pounds of sulfide passing through that system. It's more costly that way, but it is possible, because you just essentially have to use a larger system, use larger or more carbon to capture that additional sulfide. And
Yeah,
Calvin,
to expand a bit on that, carbons, it really comes down to a mass balance, right? A fixed amount of carbon will hold a fixed amount of hydrogen sulfide. So as you increase your concentration or your airflow, you're driving more mass on a time basis into the carbon, more mass of sulfide. So higher loadings ultimately burn out the carbon quicker, which results in more costs for for change outs and things like that. So how often do filters or carbon beds need to be changed? If it's anything more frequent than a year, from a service perspective, we probably wouldn't recommend carbon in that type of an application.
Mm-hmm.
And another issue to be concerned about is kind of the heat of absorption when carbon's removing sulfide or other compounds from the foul airstream. If you're driving too much absorption, too high of concentration of hydrogen sulfide and not sufficient airflow, you do risk overheating the bed and possibly starting a fire. So there are a number of reasons why you wouldn't want to do that.
Yeah, but probably in that case, just I would recommend including a T with a dampener, so you can allow for dilution air, so that way you can operate at a higher airflow, but just dilute down the concentration entering into the system.
We have a question: what method is the most reliable? And I think we're limiting it to the air scrubber specifically. So chemical scrubbing versus carbon adsorption versus biofiltration.
Well, I think all of these technologies are reliable. It's really just based on the application-specific needs and the preferences of the customer. So, I mean, for example, a chemical scrubber is very reliable, and it's very effective at removing hydrogen sulfide and or organic odors. But that type of technology might not be too useful at a lift station that's in like a residential neighborhood, for example, because having those chemicals on site might potentially cause an issue, or it might make the people who live nearby it a little bit, hesitant. So for that reason, having a more environmentally friendly or safer system like a biofilter would be preferred. But again, both of those technologies are adequate for handling odors. Calvin, did you have anything?
Yeah, and the next question kind of dovetails well into this, and that question is, when do you use a combination of these three types of vapor phase odor control? And really the answer is redundancy, right? Carbon's pretty much a fail-safe. It's going to remove odorous compounds from the airstream. Biofilters are good for knocking down high levels of H2S before going into a chemical scrubber, for example. And what that allows you to do is really optimize the amount of consumable chemical, the caustic and bleach that's fed into the chemical scrubber, and then chasing everything with carbon ensures that you just don't have any odor control issues if one of the other two odor control units were to go down or operate improperly. And I believe it's the Brightwater plant in Washington State's a great example of this in action, wherein they have a community park that runs right along the side of the wastewater treatment plant. And to mitigate having any odor complaints at all, they've done the three treatment method option to just ensure that there are no odors at that plant. And I can assure you, having been there, that you will not smell odors at that plant. Thank you, everybody, for your attention and your questions. We hope to see you at our next and final webinar.